All right, here we are again for a continuation of today's lecture, working on part 2. So continuing to look at a few miscellaneous elements of steel beam design. And what I would like to look at next is I want to consider and describe CB, which is described at the beginning of chapter F in the AISC Steel Manual. Okay. So what I'm going to describe here is found in section F1 under General Provisions. CB, what is CB? Well, CB is the effect of moment distribution on lateral torsional buckling. So usually, so let's just discuss this briefly. CB is a coefficient, and this coefficient takes into account a coefficient or just the effects of moment distribution on lateral torsional buckling. Of moment distribution on lateral torsional buckling, or LTB. So basically, if we think about this now, when we are used to designing something, so when we're consider a beam, let's consider a beam with an arbitrary shear and moment diagram, or maybe just a moment diagram for our discussion here. Let's say we have something like this, and let's say that I have just an arbitrary shear and moment diagram, maybe something kind of like this. Something kind of like this. This would be my M max here, my highest moment. Now, when we deal with say normal beam design, when we're looking at say plastic yielding or plastic section design, we're typically designing for the maximum moment. The traditional idea is, or what you've learned before, is that you look at a beam and you say, using say shear and moment diagrams from beam statics, you look at a beam and say, okay, well, where along the entire beam do I have the maximum moment applied? Where do I have the maximum moment applied? And you'll then say, okay, well, that's the maximum moment. I'm going to design the beam for the maximum moment. That makes sense. Now, in terms of plastic moment design, that is perfectly valid. In terms of plastic moment design, that does make good sense because that is a phenomenon that occurs at one particular location. But lateral torsional buckling is more of a buckling failure. It occurs over what I mean by that is, if you look at, say, a beam like this, if you have a long beam, and if at any place the moment at that place, at that cross section, at a particular cross section, if the moment at that particular cross section exceeds, or at that particular location along the beam, if that moment value exceeds what that section is capable of carrying, it will fail. It'll fail deflection, it'll fail strength, et cetera, et cetera. It might even fracture depending on how high the loading is. But when we're dealing with buckling, that is more of a function of length. So you get you can get buckling without ever reaching the maximum moment. You can have buckling, and in order to have buckling, you need to have moment all the way along the beam or spread over a long length of the beam. So it's not something, you don't get buckling when one particular element, one particular location has moment on it. Instead, you get buckling when you have a great deal of moment distributed over a large range of the beam. In order for the beam to kind of, if you think of your beam's cross-section like this, the only way it's going to just buckle out, like we've talked about previously, the only way it's just going to buckle out like that in lateral torsional buckling is if there is moment all the way along it. That's the only way that's going to work. So for example, if I had a beam that I just applied a couple to without having if I just applied a couple, for example, to a beam, in other words, if I could somehow apply just a couple or a pair of couples so that most of the beam was not under bending, only the middle section was or something like that. In that particular case, I wouldn't actually have, so for example, I could do something like this. If I had two opposing couples, through most of the beam there would be no moment except right here and right here. Those two would cancel each other out. There would be moment in this section here, but there would be no moment here or here. And so I really couldn't get lateral torsional buckling in this kind of case. I could get failure in a beam like this, but I couldn't really get lateral torsional buckling. So so this is so again, lateral torsional buckling is a function of moments along a beam, while our usual beam design assumptions, our usual beam design calculations are based across peak moment. So this is the difference. LTB is based, occurs due to moment over the length of the beam. Due to moment over the length of the beam, or along the whole length of the beam, while usual beam theory is based upon peak moment. While usual beam capacity, whether elastic or plastic, elastic or plastic, is based on peak moment. On peak moment. Is based on peak moment. So, here, so, again, now I want to look at, so we do have so this is the sort of theory behind CB, calculating CB. But I also want to look at how the code handles this. So we have this disconnect. We have our usual beam design calculations that are based on looking at the peak moment, but lateral torsional buckling, being a buckling failure, is not based on peak moment. If I could somehow apply moment to just one little piece of the beam, say like two couples like this, I would not really have to worry about lateral torsional buckling, even though I could definitely fail the section in bending that way. Okay, so CB, again, we're going to have a few values. Basically, CB is based on, calculating CB is based on quarter moments. Calculating CB is based on quarter moments. Is based on the quarter point moments. And this is just a rough way, it's not perfect, but it's kind of a rough way, but a conservative way of actually taking into account this moment distribution effect. Calculating CB is based on the quarter point moments. On the quarter point moments, so let me label something here. And so let's say this is M here. And I want to label the dimensions L over 4, L over 4, L over 4. So let's say I divide the beam up into fourths. So this would be L over 4, L over 4, L over 4, and L over 4. So I divide the beam up into quarters, and then I look at the shear and moment diagram of it, or the moment diagram, not the shear and moment diagram. So let's say we have just the same kind of generic shear and moment diagram like before. Something like this. I have moments A, B, and C. MA, MB, and MC, these are the quarter point moments. Are the quarter point moments. MA is just, so again, to find these, I look at the shear and bending moment diagram, and okay, well, whatever moment is present at the first quarter point, this is going to be MA. Whatever moment is present at the middle of the beam, this is MB. Whatever moment is present at the 3/4 point of the beam, this is MC. This is MC. And then we also have M max. That's just whatever the highest moment is. M max is fairly straightforward. That's just the max moment present on the beam. Now, here, there is one other thing to note, though. I drew all of this as positive. However, each of these are going to be the absolute value of these things. So we know that beams can have negative bending moment, especially things that go over more than one span. It's very easy to get negative bending moments, or negative curvature in a beam. So for this equation that I'm going to give you is, we'll be using the absolute values. So all of these moments, MA, MB, MC, M max, we'll use the absolute value instead of we'll use the absolute value of the actual value from the moment diagram. The absolute value from the moment diagram of the value from the moment diagram. From the moment diagram, and then we have a formula for this, and this is really the first formula, well, except aside from the, well, actually, I suppose, yeah, the first formula in Chapter F, and so it's formula F1-1, and this is the formula for calculating CB. Here, CB is 12.5, 12.5 times M max divided by 2.5 M max, 2.5 M max plus 3 MA plus 4 MB plus 3 MC. And this is just another one of those lovely empirical formulas that has come out of lab analysis that has been baked into the steel manual. Okay, so that's the basic formula, although you can find that in your steel manual, of course. And I just have on the next slide, let's give a couple finishing notes on this. So a few notes here. This is based on a few final notes. CB is calculated based on unbraced length. On unbraced length, not entire length of the beam. Not the entire beam length. Not the entire beam length. So if I had something like this, imagine I had a beam that was, say, braced. So for example, if I have a beam 30 feet long, braced every 10 feet, in that case, I would calculate 3 independent CB values. I could have three different CB values, one for each of the unbraced spans. 3 different CB values, one for each unbraced span. And however, let me show you something else though. Let's look what happens on this calculation. So again, I mentioned previously that this is based on the effects of moment being distributed. So the best case for CB, let me look at some kind of basic equations comparing the worst case and the best case. So best case for CB would be if the moment is distributed, the maximum moment occurs at a single point. The maximum moment occurs at a single point. So imagine you had a moment diagram. Now, I'd be very curious how you could ever actually get a beam that would behave this way, but this is an idealized case. Imagine you had a moment diagram somehow that it was 0 all the way along the entire beam, except at one particular location, it just went straight up like this, and that was it. You just had a single, so you'd almost have to have like 2 opposing couples or something like that. I think that's the only way I can think of to actually get it something like that to do that. That's the only way I can think of to actually physically produce a moment diagram like that. But I suppose if you really wanted to, you could. So maybe a max moment like this. How would we calculate CB then? Well, CB would equal, if I look at my equation, 12.5 m max divided by 2.5 m max plus 3 ma. So maybe this is the best case for CB. Moment occurs at a single point plus 3 ma plus 4 mb plus 3 mc plus 3 mc. All of these would go away as all of these would be 0. So I would and the m max would then cancel out. So I would basically get 12.5 or 2.5 or 5, an incredibly high value for CB. So that's really the highest it can ever get. It's never going to get higher than 5. That is the highest case. And so then after this, I'll also note where you use this as a reminder. And then let's look at the worst case for MB. So the worst case for MB, or sorry, CB, a perfectly uniform moment. So if you had a moment diagram like this, where it was just a nice, perfectly uniform distribution. Now, this makes calculating a shear and bending moment diagram easy, but in terms of moment, now, the way you could get this is, I said, well, what would actually produce this? An example would be like a cantilever with a couple at the end of it. That's how you could actually get this one fairly easily. You could have if you had a cantilever, for example, with a couple on the end of it, in that case, you would have a uniform moment diagram like that. And then our M-max equation, our CB equation, would equal 12.5, and basically in this case, MA would be equal to MB, would be equal to some MC, etc. So this would be equal to MA, equal to MB, equal to MC. All of these would be the same, just they would all be equal to M max. So 12.5 M max divided by 2.5 M max, and you can probably see where this is going if you have your code in front of you, plus 3 M max plus 4 M max plus 3 M max. And, well, let's see, 3 plus 3 is 6, plus 4 is 10, plus 2.5 is 12.5. Oh, what do you know? All the M maxes cancel out, and this equals 1.0. So CB is always going to be between 5.0 and 1.0. In the on one extreme, if all of the moment is concentrated at a single point, right where that M max is, then your CB is going to be the highest value you can ever be, which is 5.0. And then if you have a perfectly distributed moment, it's going to be just equal to 1.0. However, This also tells us that we can something that we can use, and this is very useful, especially for design. This does give us a value that we can assume. So CB generally for lateral torsional buckling. If I want to remind you of equation of F2-2, how is CB used? Using CB, if you remember, the equation for lateral torsional buckling, F2-2, uses the equation like this. The nominal moment capacity is CB times our MP minus 0.7 FYSX times LB minus LP divided by, and it also occurs in the CB also appears the same kind of way in the following equation F2-4 over LR minus LP, sorry. And then all of this is less than or equal to the plastic moment MP. Now, notice it's just a simple multiplication. It's a simple multiplier. And a higher MP, is a higher nominal moment capacity is generally a good thing. So the higher this is, the higher the moment capacity. So again, the higher the CB, the higher the moment capacity. So in other words, the more, so this is a case where the more concentrated the moment is, the better. The higher the nominal moment capacity, although we can never exceed the actual plastic bending moment capacity, MP. Though we cannot exceed the plastic moment capacity. The plastic moment capacity MP. The plastic moment capacity MP. MP here. So we can't exceed that value. But again, so again, the higher this is, the better. The lower it is, the worse. However, the nice thing about this, though, is we do have a lower bound. And because of that, we can often make a conservative assumption. There's a conservative assumption we can make, and that is that because its lower bound is 1.0, because the lower bound of CB the lower bound of CB is 1.0, is 1.0, we can then, we can conservatively, at any time, we can conservatively take it to 1.0. We can conservatively take it to be 1.0. Take it to be 1.0. And this is very useful, especially in terms of design. This is very useful for design because when you're selecting a beam, often your self-weight, for example, is going to go into the load, but you won't actually know your self-weight until you pick a section. You'll have to iterate, etc. So often, especially for the case of design, maybe not final analysis, but we can go and just select 1.0 for our CB, at least in terms of initial analysis. However, this is very conservative. In most cases, it's probably too conservative. Gonna end up with a big, heavy building if you do this for all your calculations. Very conservative. All right, but that is the basic idea of using CB, our factor for considering moment distribution in the calculation of lateral torsional buckling capacity. All right, that'll do it for this portion of the lecture, and we will be back.